So I really, well, we talked about factors holding the blood glucose up yesterday, and we talked about how the cell distributes work between aerobic and anaerobic. And the easiest summary of that last topic is to say, anytime the mitochondria is not quite up to the level of ATP replenishment that the workload is acutely supplying, you fill in with cytosolic ATP regeneration. So here's our last topic in this 3-lecture series on how does metabolism actually function in whole humans during exercise. Oh, there's review. Zach, did I do it? Did you find them? Good, okay. And there's your review today. So here's what we're chewing through. And so today, I think is really interesting. We'll begin to try to examine what factors are determining what fuels, one, two, both, fat, carbohydrate, is the mitochondria using. Okay? I want to remind you that simply because the mitochondria is burning fat does not mean your whole body fat stores will diminish. That's addressing the balance issue of in versus out by trying to just look at one side. You can't do it. We'll come back to that, I promise. But let's talk about this and go wherever you are. What's so fascinating is the way we determine the aerobic fuel mix is by looking at the RER value, that CO2 to oxygen ratio, is the way we deduce that. So I finally decided, because this is a potentially complex lecture, I'm amazed that we know this much, to be honest. So I have put up the 5, it depends on how you count 5, but 1, 2, 3, 4, and then there's 2 subsets in 2 of them. So it's somewhere between 4 and 6 factors. But these are all the factors that determine mitochondrial fuel mix. Okay? Diet influences in 2 ways. The first one is the chronic level. This would be over days, 2 to 3 days. The amount of carbohydrate in your food will either enhance or limit your ability to replace the glycogen you used in the last workout. So a carbohydrate-rich diet is important for athletes who work hard. The second way that diet works, and this is the one that has to do with rest, I'll show you in a moment. If I say, I measure a respiratory exchange value in someone who's simply resting in a recliner in my lab, and the value is 0.85, what do I know about when did they last eat?
Recently?
Probably within the last 3 to 4 hours, they had a meal that was mixed in carbohydrate and fat. Does that make sense? So your fuel will tend to shift towards whatever your last meal was, and that effect usually lasts between 2 to 4 hours, and then slowly, where does the R value go as the time since your last meal goes on? 0.7. So those of you observing Ramadan, by the time you get to the evening, to the sunset meal, boy, do you have an R value of 0.7. That's one of the problems. That's why it's so hard. So those are the first 2. Then this is the elephant in the living room, and we'll talk about this greatly for 4 or 5 slides. The harder you work, the more you must use carbohydrate in the mitochondria. By the way, notice you'll also be using more carbohydrate in cytosol, because if you're working really hard, you'll tend to have a bigger oxygen deficit at the beginning of that workload, right? So all forms of carbohydrate, whether it's anaerobic or aerobic, go up. This one, we've just talked about oxygen deficit. When you start exercise, the closer when you initially bump a workload up, whether it's from rest or from workload number 1 to workload number 2, the anaerobic systems will fill while the mitochondria speeds up, because it takes longer. That make sense? We'll talk about this one next time, or at the end of this hour, we'll talk about how if you do sustained single load work, if fat can meet the ATP replenishment need, you'll tend to stop using carbohydrate and save it for high intensity work. And this is an interesting biochemical phenomenon called the Randall shift, but let's wait till the end. And then this is where we're headed. Starting on Monday, we'll talk about how does training change mitochondrial metabolism. And I'll give you the big overview. The more you train aerobically, the more your metabolism shifts away from anaerobic towards aerobic. So tell me, what do you think happens to the oxygen deficit at the onset of work if you've doubled your mitochondrial supply in the muscle? The oxygen deficit shrinks because you reach the steady state oxygen faster. Then within the mitochondria itself, the oxidative use shifts away from carbohydrate and toward fat because you've expanded the total amount of ATP you can replenish based on fat, and to spare, because this is your high energy fuel that you have the least of. And so you're actually sparing the glycogen. It lasts longer, or you just put off using it until there's a true emergency. That's a huge amount of metabolism. That one slide is my entire graduate course in metabolism when I was a grad student. Let's go into the detail. This is fun. I was looking at this. This is the energy sources at different work intensities. Pink colors, versions of pink, have to do with lipids, and that's intramuscular lipid and free fatty acid. Gray colors have to do with either stored muscle glycogen or plasma glucose, so these are glycolytic sources. Everyone following? Let's do rest first. So, did these people who did this study, were they weighting, it seems to be 60% fatty acids and 40% carbohydrate, did they make these measurements first thing in the morning after the patient had been fasting since bedtime? No. They brought the person in midday when a meal had been within the last couple hours, because this is balanced. Okay, now let's look at exercise. Light work, we see the amount funded by fatty acid goes way up, looks like it about triples, and the blood glucose is not greatly dinged, but muscle glycogen becomes a significant. You always choose your glycogen over blood glucose if you can. Okay, go to a higher workload. Fat oxidation goes up again, but not nearly as much. The blood glucose is now actually starting to be tapped into at levels much greater than resting, and the muscle glycogen is getting bigger and bigger. This is interesting, and that's what we're going to talk about next. Look what happens to total fatty acid use as you go to high intensity. From here, it actually decreases in the total number of calories. We'll look at some of the mechanisms, but you know the easiest way to think about this? If you're demanding that ATP be replaced at 5 millimoles per, I don't remember the units, millimoles per kilogram. That's how fast you need it. And the top speed of this is 2.5 millimole per. Guess what you do less of? This is simply being out-competed. You've got to use an energy system that can replace the ATP at the same rate as being used up. Tracking all that? Okay, be brave. There's 5 more slides on there. So this data here, I think the reference is down here if you want to go look at the original. It was one of the, almost certainly the Belgians did a whole bunch of really invasive studies where they actually cannulated arteries and veins to track these nutrients. It's very cool. But we're not going to do it again because it was reasonably dangerous. So this data here, if you don't like how that looks, this is just regraphed here. So you see fatty acid relative to rest will double and perhaps triple in light work. As you go towards intense work, fatty acid oxidation drops off and is supplanted by blood glucose and muscle glucose sources that have higher total rates of ATP replacement. Okay? This is what, so by the way, this is kind of funny. So is there a fat burning zone? where fat is the predominant fuel? Yes, there is. Okay, here's the drawback. Exercising in that zone does not guarantee you'll lose fat. Let's say I do 10 minutes of work and I use 10 kilocalories of fat when I'm ingesting 130 each day. Are you with me? And remember, the total calories count because any carbohydrate and protein in excess can quite nicely be used to resynthesize fat. So the fuel used during exercise is not, to be quite honest, in terms of weight loss, you'd be far better if you just had 20 minutes to do a workout. Go hella hard, burn almost exclusively glycogen, and then if you actually want to lose weight, don't replace all the calories you burn by eating. That's a lot easier said than done, but that's what creates weight loss, or calorie deficits. So let's see. Fat as a predominant fuel just isn't fast enough to support ATP replacement for contraction at intensities higher than about 50%. Got all that? Okay, let's go further. Oh, this is showing in this little figure, I shouldn't figure out what this was. It's just reminding you where fat comes from. The vast majority of it is coming from adipose tissue. We have a little startup fund in our muscle of intramuscular triglycerides. It's a startup fund. All right. So the next two slides are going to talk about how do we enhance fat metabolism as we start exercise. By the way, if you hike for a day, right, an 8-hour hike when you're backpacking, hella calories of fat burn. You almost notice your friend's breath is a bit fruity at the end of the, little bit acidotic at the end because you use so much fat. Low intensity sustained work rocks. Again, you can't expect to lose fat unless you didn't bring food in your backpack. So just to remind you, how would we increase fatty acid metabolism to get from resting to maybe a tripling in moderate work? First off, the epinephrine that's being secreted stimulates hormone-sensitive lipase to break down triglycerides and put fatty acids into the bloodstream. This is review. Then the fatty acid transport protein, that's often called fat, brings it across the membrane. And remember that fat is upregulated by contractions. So it's very much like glucose. Put more in the bloodstream and add more transporters in the working muscle. Then the fatty acid binding protein brings this into the carnitine palmitoyltransferase series of enzymes. And this also, if you remember, CPT1, you guys look it up to be sure I know what I'm talking about. I seem to remember it is stimulated by calcium. So this also will start to increase. So when you add up more substrate, more uptake, more entry, yeah, there you go. So that's where your increase comes from, and I find that to be the least puzzling of responses. Why do we use more fat when we exercise? We need more total calories. As long as the rate of work is within the range of what we can replace, that's what we use. So this part of the curve, as I look at all this, it's that's the weirdest. This I understand perfectly, epinephrine-driven glycogenolysis. This I understand perfectly, GLUT4, calcium-stimulated uptake. This I understand, I just talked about it on the last slide. That is weird. Right? Why is it that fat as a total fraction of calories starts to fall off at high intensity? Well, I think the easiest way to look at this for a beginner, and I promise you can have graduate courses. I'm so glad. So, Satender, this is Katam, so I will need that.
Did yesterday's one?
I haven't checked it yet because I left the flash drive I just got that. So hooray for you, because this is once again not reliable. So I think the easiest way for you beginners to think about this change in ratio is basically fat oxidation gets outworked. That if the mitochondrial oxidation of glucose, remember they just have one enzyme to get it in, PDH, it's immediately TCA ready because pyruvate dehydrogenase makes it to acetyl-CoA. You're immediately ready, whereas that long step of beta oxidation where you're snipping off 2 carbons at a time to get them, that takes a lot of time. As well as the membrane transport both into the cell and into the mitochondria. There's a lot more steps. So one way to think about this is simply fat oxidation gets out-competed. There are actual levels, or actual epinephrine release does enhance fatty acid recruitment, but it increases glycogen breakdown even more. So if you start to really push the epinephrine levels, fatty acid oxidation will go up slightly, but glycogen breakdown will go up a lot. Let's talk about that a little bit more. There are some biochemical reasons. By the way, we were talking in office hour today about if you're using the RER, the respiratory exchange ratio, say the person comes in and has a value of 0.7 at rest. Rest is not on here, but if rest was here, person's fasting, and they might have an RER of 0.7. That would imply 100% fat to start. You start them exercising, there will be an increase in fat metabolism, but the fat metabolism may double, but carbohydrate metabolism will triple. And so you start to get this. Now, the further you increase the workload, you see the fat metabolism as a fraction of the total mix drops. So the carbohydrate metabolism continues. When I say repeatedly carbohydrate is our high intensity fuel, that's what I'm talking about. Oh, by the way, just as an interest, we were talking about this in office hours. Can you guys guess? We haven't talked about training effects on the mitochondria. That's Monday's topic. But if I were to tell you that one of the training effects is to use as little carbohydrate as possible because it's your premium fuel, so at any workload, the training effect is, oh, I'm saving this carbohydrate and I'll use more. Can you guess what that's going to do to this curve? You'll use more fat at any submaximal workload and less carbohydrate. So the lines will shift. They'll still travel on the same basic pattern, but they'll tend to this point of crossover will be later at a higher workload, and very often the total workload is actually increased. Your metabolic capacity increases, and you hold off using your precious glycogen until higher. Sir?
So when we've thrown out the over 60% VO2 max, you'll tend to use carbohydrate. Could that not be true for really aerobically trained?
Yes, yay! So this is flexible, in other words, Moses. So it looks like this person has been in bed for quite a long time because they don't have a very late crossover. The more the person trained, the more this marches out. Perfect. Yes. So it is flexible. As far as the actual, if you look at, so again, trying to explain why does fat metabolism drop at the highest level of exercise. There are systemic issues that blood flow to the fat pad actually decreases when you go to high work. You clamp off the skin, you clamp off the gut, you clamp off the adipose tissue in terms of blood flow. So you cease to flush out as much fat. So delivery drops. This second idea is inside the cell. See if I can describe this. And if the rate limiting step is carnitine palmitoyltransferase, you can actually start to have a problem with both the energy state and carnitine, which is shown here. If large amounts of acetyl-CoA are arriving due to glycolysis, you'll get an overabundance of citrate. So you have more citrate than the TCA cycle easily handles. By the way, if that's the TCA cycle, that's the cytosol. Good. So pyruvate comes in. If you have an overabundance of citrate, citrate will actually go through a reaction to malate, malonyl-CoA. Does anyone see it? There it is. Malonyl-CoA, there's a series of reactions here. Malonyl-CoA is actually directly inhibitory to fatty oxidation. So once again, if you're having more glycolytic substrate, it tends to turn off your fat oxidation. So to some extent they're competitive, particularly when you're getting a hormone-driven breakdown of glycogen inside the cell. You can chew on that. I probably won't ask you a lot about it, but the acetyl-CoA carboxylase is creating malonyl-CoA, and that's inhibited your fat import. That's about the hardest thing we'll do today. The second thing that might slow down the carnitine palmitoyltransferase enzyme, besides malonyl-CoA, is remember you need some carnitine to be involved over here. And I believe what happens is, and this is sort of right at the edge of my abilities, if you're starting to deacetylate your carnitine in order to create lots of acetyl-CoA, you start to get a premium on acetyl-CoA, and you wind up with an insufficiency of activated carnitine to come to fat transport. So once again, it's similar argument to the other one, that you're dealing with limited amounts of intramitochondrial resource, and the more you devote to glycolysis, the less there is available for fat oxidation. Is that okay? Not too crazy? All I was trying to do was explain the last 3 slides. That. And part of that really is restriction of blood flow to the fat pad. That works too. That's easy. That's what I believed for the first 3 years of my career, because it was easier to remember. There's also cellular reasons that happen. Oh, look at this. So as we start to talk about, we'll go next to the higher intensity stuff, and I find that to be easy. So catecholamines do stimulate fatty acid breakdown, glycogen breakdown, and liver breakdown of glucose. In terms of the magnitude of the response, it tends to be curvilinear. So that at the higher work intensities, you really start releasing a lot of epinephrine and norepinephrine, and these tend to enhance glycolytic flux greater than they enhance fat breakdown. Okay, so good time to pause for a second, shake out your hands. Any questions about that so far? I'm not sure how much you have to know the details. I think the big point was fat is your infinite low-intensity fuel. Sorry to say infinite. Fat is your infinite low-intensity fuel, and carbohydrate is your limited high-intensity fuel. Is one way to summarize the outcome. So the next 6 slides are going to talk about if high-intensity exercises uses glucose, let's first prove that, and then think about what some of the outcomes of that are. So here's the total. This is, again, one of these very invasive Belgian studies that are just great, where you're looking at direct leg glucose uptake by monitoring femoral artery versus femoral vein glucose concentrations, how much disappears, what went into the muscle. So notice there is an increase from rest at light work. Where you really see the huge increase is with heavy work. So we saw that with light work, you might double your GLUT4 receptors within 20 minutes, and that's what you're seeing there. As you go to really high intensity, you see that glucose uptake out of the bloodstream goes way up. Remember, glycogen is also being broken down at the same time, and as long as you have lots of glycogen, you'll tend to favor that and not ding the blood glucose, which really should be for the brain. So here's the other side of that coin. The same figure, but instead of blood glucose, you're looking at the muscles glucose being used up. And you notice how I've said you have something like an hour to 90 minutes. Well, it depends on how hard you're working. The harder you're working, the more total glucose you're using, all right? So notice, if you work at 85% of VO2 max for 60 minutes, have fun with that. It's very unpleasant. Actually, it's kind of fun until the last 45 or 15 minutes, and then it sucks. But notice, you'll come very close to complete depletion in an hour. If you take it slow, this is me running a marathon. If you take it slow, you can make it all the way to, my fastest marathon is 3 hours and 20 minutes. I'm not highly aerobic. So it'll last for the duration. Making sense? So the rate at which you run out is dependent on how quickly you use it. And we had this nice example in terms of blood glucose that once you use up all your, if you do this workload and do not have a source of supplemental glucose, you are not going to go much, the next half hour is going to be horrible and you're going to quit because you've run out of glycogen and glucose. So this was our example at the end of last lecture. Once you completely deplete the muscle supply of glycogen, the muscle will progressively tap into the blood glucose and eventually that becomes limited. Whether it's muscle dysfunction or brain dysfunction or both, that's what's going to happen. So let's talk a little bit then, this is sort of continuing our discussion from last time of, so how do we defend carbohydrate if it's our most precious fuel? The first one is, after a depletion event where you use up all the glycogen, so this is, I run a 90-minute, or I play a 90-minute soccer game, if you try hard, you come pretty depleted. This is stained for glycogen. And afterwards, you take in carbohydrate, and a large amount of that is redirected into the muscle. And generally, after depletion, you get a rebound supercompensation. The theory being the body is basically glycogen synthase is saying, oh my gosh, we almost ran out last time, we better add 20% more in case she goes out and does that again. Are you with me? Really nice study done. So this is, I always try to, whenever we reach something where putting something in your mouth actually works and has a huge effect on performance, I should probably jump up and down and go, hey guys, this is stuff you'd be wanting. So I will do that now. This is a study in which the same subjects exercised to exhaustion on separated, these were separated by several weeks. And they would first feed on a regular carbohydrate diet, right? Then they would do time to exhaustion. So they exhausted at a little over 2 hours on a medium carbohydrate diet. And their, oh, sorry, I got that. Oh, their muscle glycogen was here, and they exhausted here. They were then put on a low carbohydrate diet, like Atkins, or what do we call those these days, the ketogenic diet. And notice, their muscle glycogen has been almost dropped to a third of what it was, and so too their exercise time drops. Okay? And then, when they're repleted with a high carbohydrate diet, notice how high they're willing, the muscle's willing to go. And that indeed extends endurance time. So this is, in terms of, if you're going to be a high-intensity endurance performer, you need a lot of chronic carbohydrate in your diet. If it's not above 50%, you're not eating it. It should be up there on 60, 70% of your diet. Lots of carbohydrate. Is everyone tracking that? Yes, sir.
Then why do so many ultra-endurance runners go ketogenic and then hyperload carbs?
Yeah, let me try to help. So,
like, is that, are they
first off, notice my dropping shoulders. If you're an average Joe or Josephina blow, I would never do that. If you're an elite athlete, you might think about it. What they're trying to do, Moses, is train their mitochondria. And it is true, if you train in a ketotic state, your mitochondria will elaborate more enzymes of fat metabolism. So they're trying to up their fat metabolic capacity, and then on top of that, they're going to put on the carbohydrate afterburn. And
so this is more like a single bout, what's on the graph?
Yeah, this is a single bout. Let's see if I can go back far enough. What they're trying to do with that intervention is the idea would be the ketonic training will lift this up and perhaps get it out a little further. So you have a little bit more fat reserves. At the same time, then with glycogen depletion and reloading before the event, you'll advance this. And so they're trying to get this entire curve to go up to create higher levels of sustained endurance output. Again, this is very fancy new stuff. You know the term biohacking? Mm-hmm. I hate that term. I have to say that strikes me as the stupidest possible thing to do, is try to outsmart 120 million years of mammalian evolution. That just sounds really stupid to me. So, sorry, if I'm not into the extreme methods. I think the extreme methods backfire a lot. I want you to complete a half marathon while ketotic and then come talk to me. I've done it. It's hell. So it's not fun at I need to tell you a story about how effective this is, because you would think that this is common knowledge. So there may be a reason to train in a glycogen depleted state if you do your competitive events in glycogen depleted state. I have to say there is no data, Moses, that you couldn't get the same or better effect by simply taking some glucose during your competitive event after the first hour. There is no data showing superior. So a lot of this superiorness of ketotic diet for training is theoretical. It's not demonstrated. A demonstrated, it's just a great study. You know, now we've got these little vests that have GPS and heart rate and all, there was a study done on the European Soccer League, and a lot of Real Madrid players, a lot of players from there, and they wore a vest, and you could actually track their total distance run and the total speed run for an entire match. Now, unbeknownst to them, so it's a single blind study, they were asked to monitor, to do diet records as they went through the season. Then the nutritionist analyzed the diet for carbohydrate, percentage carbohydrate, and compared that with second half speed and distance. Remember, second half is after 45 minutes. Anyone want to tell me how the study turned out? Those with the highest levels of carbohydrate intake ran faster and further in the second half. Those with the lowest levels of carbohydrate, they futzed out. You could actually watch their speed and distance drop as the second half progressed. What astounds me is, these are professionals. Wouldn't you think they knew that carbohydrate was important? You know what I mean? So I found this study was completed about 2010, and it strikes me that, again, that we're all going into this sort of extreme physiology kind of stuff, hoping for improvement, and forgetting the basics. No carbohydrate, no running in the second half. So I thought that was and that's a real concrete human result in a practical competitive environment. So for me, I have messed with ketosis as sort of a one-dog study. If Song is here, we've talked about one-dog studies. But yes, Dylan.
On that study, did they test people in all different positions or just like forward and
They tested everybody because, as you know, they have different running characteristics. But yeah, boy, if there's one position that can neglect their carbohydrate, it's the goalie. And if there's one position that needs to be chucking down the pancakes, it's the halfback. You've got it. Very good. Okay, second defense for our premium intensity fuel is the liver can make new glucose. It will tend not to do this until quite late in the work. So this is something, if you've taken no carbohydrate and you're 90 minutes to 2 hours into the work, you're beginning to run out of muscle glycogen. Your muscle is sucking the glucose out of your bloodstream, and your brain is starting to suffer. Mother liver to the rescue. Remember, the liver takes care of all the other organs. And so what the liver will do is begin to resynthesize new glucose from 3 carbon goodies. And we'll talk about this for the next 2 slides. So first, to show that the glycogenolysis first, and then we'll do this rare thing, gluconeogenesis. But glycogenolysis, remember, the liver has glycogen, and that glycogen is for the bloodstream, not for the muscle. I mean, that's how it should be. And so here's the liver's output. Again, you can get this from catheters shoved into the hepatic vein, things that we don't do a lot of these days. But notice that the harder you work, the greater the rate of glucose breakdown. And if you were to graph this, notice how it's kind of curvilinear. Let's see, a 20% jump in VO2 max made that little change. A 15% jump in VO2 made a bigger change. And then a 10% jump made a triple change. So this, if you graph this, this is, again, a curvilinear response, basically to epinephrine. Sure?
Do you use muscle glycogen or liver glycogen first?
So again, they're different. You use them simultaneously, but the muscle glycogen can only feed the muscle it's in. It only goes to its own muscle cell. Incredibly selfish, not available for the general population. That is for the bloodstream. So the liver only drops it into the bloodstream, and the muscle may grab it. This, I have to say, gluconeogenesis is almost more of a starvation thing than it is an exercise thing, but it does help exercise. Oh, so let's look at the hard one, gluconeogenesis. Again, this is all Morgan Feelig, Belgian invasive data when I was in grad school or medical school. And showing that here's gluconeogenesis, here's glycogen breakdown from the liver. These are both liver phenomena. Notice that at rest, there's hardly any gluconeogenesis, and if you're topping off, if the person's fasting, you're topping off the bloodstream with liver-stored glycogen from the last meal. As you work, glycogen breakdown goes up hugely, and gluconeogenesis almost not at all, until you get, someone divide that by 60, I don't do math, to the 4th hour. In the 4th hour, you'll notice you're starting to run out of liver glycogen, and so you greatly enhance gluconeogenesis. There are people who train for this too, Moses and Dylan and other folks who train their gluconeogenesis capacity of the liver. You do that by completely depleting your glycogen and then continue to run, not in a very straight line, I have to add. And again, I'm okay with that, but my retort is always, why don't you just take a goo packet? How is the liver making this additional glucose? Lactate and pyruvate are both tricarboxylic acids, 3 carbons on a carboxylic acid. When these get to the liver has the specific synthetic enzyme pathway to take 2 3-carbon goodies and make them into a 6-carbon goodie. So that's unique to the liver, the ability to take, it's also, by the way, the only way that the muscle can actually contribute to the body is, you know how we said like some fibers overmake lactate? Well, nothing's wasted. This goes in the bloodstream, and it's actually a way to transfer high-energy molecules out of the muscle. It's the only way to transfer high-energy molecules out of the muscle. So that one is called the Cori cycle, when you take lactate and make it into another 3-carbon. You won't not really have thought of this, but alanine is a 3-carbon amino acid. 1, 2, 3. I did it. And if you were to deaminate this, the liver has many, many deaminating enzymes to cut that, you would wind up with a 3-carbon moiety in the liver. There you go. You transfer the amine onto glutamate through the, I've lost the name of that enzyme, but I know it, I've measured it. And then you're again, you have 2 3-carbon molecules that you can make glucose out of. So those are the 2 ways that this is often a famine. You know how in famine, if you're truly not eating, you begin to consume your muscle. And here's one reason to consume your muscle. It provides a substrate for maintaining your blood glucose beyond the 3rd day after you've run out of glycogen. Is that okay? Very good. So to finish, nice. In fact, I may not push you too hard. I'll get you to an overview, and then the last concept's a little tricky, so I think I'll let you base. Let's do three more slides, maybe, quick. So, don't look at this side yet. This is Fred Coyle data, where people are cycling to exhaustion. Here's 3 hours. Notice what happens in terms of, and so if they're going at 3 hours, it's fairly low intensity, 70% VO2 max, because otherwise you can't do that, right? If it was 85%, they'd be done here. So it's a lower intensity. This is the equivalent of a 3-hour time trial on a bike. So notice in the early part of exercise that fair amount of lipid, most of the glucose being used is muscle glycogen, right? Then as you, let's go to an hour. As you go beyond an hour, you're starting to drop the muscle stored glycogen, and so the fraction, especially as you go beyond the 2nd hour, the fraction of muscle glycolysis that's coming out of the blood is quite high. Are you seeing that? And notice the glycogen is continuing to drop off. They basically quit. By the way, see how this gets really big? This is going to be where they get hypoglycemic. They drain their blood of glucose, and they quit. So can anyone think of a behavioral intervention that would somehow prevent that quitting point? Yeah, put something, this is one of the few times that putting something, notice it's something that we had, Neanderthal had dried fruit or pieces of polar bear liver. I don't care where you're getting your carbohydrates. It's a natural intervention to drop in some glucose. So that's what this is. And these people are taking roughly, after the first hour, you're adding roughly 100 calories per hour through the mouth of nearly pure sugar, glucose. And notice what it does. You still have the same glycogen depletion curve. You can superimpose these. You're still running out of glycogen just as fast, but what you've done is you've opened a new port that is allowing the plasma glucose to be taken from without draining. That's hard to say. So I've shown you these figures. You might want to download these things back to back. I think I've shown you 3 of them. This is the 4th in a series, and kind of compare them. So this is the one where Elisa was asking about the situation that leads to the draining of blood glucose. And we saw that usually it takes hours, plural, of exercise to get to a point where the amount of total glucose being released is not keeping up with the amount of total glucose being used. And this requires that, let's see if that will work. So there's your mismatch. And that requires, part of the problem is this port for muscle glycogen is running out. You don't have enough muscle glycogen to keep the muscle going, so it starts tapping from the bloodstream to the tune of about, looks like it's off by what, about 20 grams per hour? Well, if you could arrange that something like 20 grams per hour of glucose was coming out of the GI tract and back into the blood, you perfectly offset this problem. Does that make sense? And so after the first hour, glucose support is tremendously useful. And I've just done, I went and did the math for you based on my own glucose consumption rates. If it's around 100 calories, how many calories? Let's see, that would be about 20 to 25 grams, wouldn't it? See how it all matches up? So something like 20-ish grams or 100 calories per hour after the first hour is a very powerful intervention to sustain long-term work. Is that okay? Has anyone here ride their bike enough to have bonked, if you know that term, bonk? Bonking is exercise-induced hypoglycemia, and boy, does this work. You think it's really important to carry an extra tube in your saddlebag. It's probably at least as important to carry an extra power bar in your saddlebag, because both of those things can leave you by the side of the road. All right. So here's what we've said so far, and let's quit after this one to keep it, because the next topic is a little tricky. So, if you're fasting, what metabolism will you be running on? What will your mitochondria be using as an oxidative source? Fat. Good. How about you have a meal? What will your mitochondria use? You'll tend to use the energy balance of that meal. Right? If there's a lot of, I was teasing today one of the folks, if you went to IHOP, ate pancakes with no butter, and then drank all the syrups on the table, there's all those different syrups, your R value would be 1.0 for the next 4 hours, and you would be using, your mitochondria would be using glucose because there was so much of it. Make sense? All right, then, as you go into light exercise, if you've had a meal, or you're going to do light exercise, gentle exercise, fat is going to be your main substrate. Remember, as you go longer, several things that will enhance fat oxidation will increase through time. So this is your hiking on nearly pure fat that gets you to the next source of food. We ate all the mangoes in this valley. We now have to hike over the Brecha de la Vieja into the next valley. I've suddenly become a Quechua, I don't know why. But you're an Inca and you're hiking into the next valley to find a new mango tree. Yeah, that's all. Then, as exercise intensity increases, the fraction of energy that the mitochondria derives from carbohydrate increases. Somewhere between 45 and 60% VO2 max, you start to have a matching of 50% of the fuels coming from carbohydrate and 50% from fat. High intensity exercise, both anaerobic cytosolic glycolysis and mitochondrial use of carbohydrate skyrocket. And so if you're working hard, like in a soccer game, you may 80% of your energy output is probably using carbohydrate as a substrate. And that, again, that's why you got that result in the European Pro study, that the people who have the most substrate at the beginning have the fastest outputs at the end of match. Does that make sense? I think that's, God, that's so much more than I had to learn as an undergraduate. I'm so sorry about, you know about scientific knowledge doubles about every 25 years? So in my career, that means you're now getting like 3 times as much. I'm so embarrassed. I try to do a good job to summarize, and that's enough.